What if I told you that separation is an illusion, not metaphorically, not spiritually, literally, mathematically proven? Two particles on opposite sides of the universe can remain instantly connected, no matter the distance. Einstein called this spooky action at a distance because he refused to believe it. But in 1964, a physicist named John Bell did something remarkable. He proved Einstein was wrong. And the proof is so elegant, so simple, that it forces us to question the very foundation of how we understand reality. By the end of this video, you'll understand why the universe cannot be made of separate, independent parts. And you'll see why this matters, not just for physics, but for how you understand your place in existence. Einstein believed the universe operated through clear, local causes. Objects could only influence what they touched. Information traveled at the speed of light, no faster. Anything else would break how reality works. He wasn't being stubborn. He was protecting something he'd spent his life building. A universe that made sense, a universe where things made sense, where cause and effect were connected, where distance meant something. God does not play dice, he famously said. He believed the universe followed rules. It wasn't random. It made sense. So what terrified him so much? Quantum mechanics suggested something that violated everything he believed. Two particles, separated by any distance, could remain instantly connected. Measure one, and the other responds immediately, even if it's on the other side of the galaxy. No signal, no mechanism, just connection. For nearly 30 years, this remained a philosophical debate. But Einstein never got to see the answer. He died in 1955, still unconvinced, still arguing that the universe had to be rational and local. Then, in 1964, 9 years after Einstein's death, something remarkable happened. A physicist named John Bell, not famous, not celebrated, working quietly at CERN, decided to tackle the problem that everyone else had given up on. Bell was different. He didn't accept the conventional wisdom that the question was unanswerable. He sat down and asked a simple question. If Einstein is right and hidden variables exist, what would we actually observe in experiments? What would the data look like? The answer he found was elegant, beautiful, and devastating. Bell turned Einstein's philosophical argument into a testable mathematical proof. And when scientists finally ran the experiments, they discovered something that shattered our understanding of reality itself. To understand why this matters, we need to understand what Bell actually proved. And it starts with two assumptions about reality that seem obvious until you test them. Bell's theorem is a mathematical proof that demonstrates the universe cannot be both local and realistic at the same time. But first, you need to know something. These two assumptions seem so obvious that most people never question them. They seem like common sense. And that's exactly why Bell's proof is so devastating. Let me break down what that means, because this is where quantum physics stops being abstract and starts challenging everything we think we know about existence. Locality is the assumption that objects are only influenced by their immediate surroundings. If I'm in New York and you're in Tokyo, nothing I do right now can instantly affect you. Any influence has to travel through space, and it can't move faster than light. This is the bedrock of Einstein's relativity. It's how we understand cause and effect. It's common sense. Think about it this way. You can't affect your friend across the world without sending a message, a letter, a phone call. Something has to travel. Nothing happens instantly. But then there's realism. Realism is the assumption that particles have definite properties whether we measure them or not. Adding pattern interrupt 3, Bell's inequality inserting numerical anchor and stake statement to make the technical explanation more concrete and tangible. If the particles are following local hidden variables, there's a specific pattern you should see. Bell derived an inequality that puts a mathematical limit on how often the measurements should match. This limit comes directly from assuming particles carry predetermined properties and can't communicate faster than light. For certain choices of angles, Bell showed that if local realism is true, the correlation between measurements at angles A and B plus the correlation between B and C must be greater than or equal to the correlation between A and C. If the particles are following local hidden variables, there's a specific pattern you should see. Bell derived an inequality that puts a mathematical limit on how often the measurements should match. This limit is 2. That's the maximum correlation value if Einstein is right. In other words, if Einstein was right, the numbers should obey this rule. For certain choices of angles, Bell showed that if local realism is true, the correlation between measurements at angles A and B plus the correlation between B and C must be greater than or equal to the correlation between A and C. A coin has a specific side facing up, even if no one looks at it. The moon exists when no one observes it. Properties are real, independent of measurement. Again, this seems obvious. Einstein believed both locality and realism had to be true. Quantum mechanics, in its standard interpretation, violated locality, so Einstein proposed that quantum mechanics was incomplete. He suggested particles carried hidden variables, secret instructions that determined their behavior in advance. These hidden variables would restore both locality and realism. The particles only appeared to be connected because they were following a prearranged script. This is where Bell entered the story. He asked a simple question. If Einstein is right and hidden variables exist, what would we actually observe in experiments? He derived an inequality, a mathematical limit on how strongly two separated particles could be correlated if they were only following local, realistic rules. Think of it like this. Imagine two people, Alice and Bob, who each receive a box with a red or blue ball inside. They open their boxes in separate rooms. Sometimes the colors match, sometimes they don't. If the balls are just randomly assigned before the boxes are sealed, following local, realistic rules, there's a mathematical limit to how often the colors can match across many trials. Bell calculated that limit, but quantum mechanics predicts entangled particles violate Bell's inequality. They show correlations stronger than any local, realistic theory allows. Not by a little, by a lot. The quantum prediction is clear. If you run the experiment, you'll see correlations that are impossible under Einstein's worldview. This is the power of Bell's theorem. It's not a philosophical argument. It's a mathematical proof that makes a testable prediction. Either Einstein was right and experiments would obey Bell's inequality, or quantum mechanics was right and experiments would violate it. One of them had to be wrong. And here's what makes this so profound. Bell proved that if quantum mechanics is correct, then either locality is false, or realism is false, or both are false. The universe cannot operate the way we think it does. Separated things cannot be truly separate, or properties don't exist until measured, or both. When scientists finally ran the experiments in the 1970s and 1980s, the results were unambiguous. Bell's inequality was violated. Quantum mechanics was right. Einstein's vision of a local, realistic universe was wrong. The implications are staggering. This isn't about particles behaving strangely in a lab. This is about the fundamental nature of reality. It suggests that at the deepest level, the universe is not made of separate, independent objects. It's an interconnected whole. Distance, as we experience it, may be an illusion emerging from something more fundamental. Einstein refused to accept this. He had a solution: hidden variables. But when Bell examined that solution mathematically, he discovered something Einstein never anticipated. This isn't just a technical detail. It's the heart of the debate about whether reality is fundamentally connected or fundamentally separate. Imagine you have two coins that always land on opposite sides when flipped. You flip one in New York, it's heads. Your friend flips the other in Tokyo. At the exact same moment, it's tails. Every single time, without fail, they're opposite. Now imagine doing this 1,000 times, 1,000,000 times. Every single time, without fail, they match perfectly. No mistakes, no exceptions. Your friend never calls you to coordinate. There's no hidden signal. Yet somehow, impossibly, your coins know what the other is doing before either of you even looks at them. The quantum explanation says these coins are entangled. They don't have a definite state until measured. The moment you measure one, the other instantly becomes the opposite, no matter the distance. This is non-locality. It's instant connection across space. It's also completely, utterly impossible, according to everything we thought we knew about how reality works. Einstein hated this. He proposed that each coin secretly carried instructions from the moment they were created, a pre-programmed script determining the outcome in advance. The coins aren't communicating, they're just revealing information that was already there. This sounds reasonable. It makes the universe predictable and follows rules. It makes the universe knowable and rational again. It's an elegant solution, but Bell proved it doesn't work. Here's why. If hidden variables control everything, there's a mathematical limit to how strongly two particles can be correlated. Think of it like this. If two coins are pre-programmed before they're separated, there's only so much they can match. But quantum mechanics says they match more than that limit allows. The correlation is too strong, too perfect. So either Einstein was right and hidden variables don't exist, or hidden variables exist but they're not local. Something has to give. But Bell proved something devastating. Any theory based on local hidden variables makes specific, limited predictions about how strongly particles can be correlated. And those predictions are weaker than what quantum mechanics predicts. Bell calculated that limit mathematically. It's not arbitrary. It follows directly from the assumptions of locality and realism. Quantum entanglement exceeds that limit. The correlations are too strong, too perfect, too synchronized. They violate Bell's inequality in a way that no local hidden variable theory can explain. Einstein's solution doesn't work. You can't save locality and realism by adding hidden variables. Either the particles are genuinely influencing each other faster than light, violating locality, or properties don't exist until measured, violating realism, or both assumptions are wrong, but you can't keep both and explain the data. This is why Bell's theorem is so powerful. It doesn't just say quantum mechanics is weird. It proves that any attempt to make quantum mechanics less weird by adding hidden variables fails. The weirdness is unavoidable. Non-localism or non-realism, or both, are features of reality itself. The universe, at its foundation, cannot be explained by local causes and pre-existing properties. The idea that things are separate and independent breaks down at the quantum level. And since everything is made of quantum particles, this isn't just about the microscopic world. It's about the nature of existence itself. Now here's where it gets brilliant. Bell didn't just say hidden variables don't work. He proved it mathematically. And the proof is surprisingly elegant. Bell imagined a specific experimental setup. Alice and Bob each receive an entangled particle and can measure its spin along one of three possible angles, A, B, or C. They randomly choose which angle to measure for each trial, record whether the result is spin up or spin down, then compare results across thousands of trials. If the particles are following local hidden variables, there's a specific pattern you should see. Bell derived an inequality that puts a mathematical limit on how often the measurements should match. This limit comes directly from assuming particles carry predetermined properties and can't communicate faster than light. For certain choices of angles, Bell showed that if local realism is true, the correlation between measurements at angles A and B plus the correlation between B and C must be greater than or equal to the correlation between A and C. This follows from pure logic and probability theory. But quantum mechanics predicts something radically different. Entangled particles violate Bell's inequality in ways no local hidden variable theory can explain. Quantum entanglement produces correlations that are impossible under local, realistic rules. Think of it like three light switches that sometimes turn on together and sometimes don't. If they're just randomly assigned before you look at them, there's a mathematical limit to how the patterns can work. Bell's inequality captures that limit. Quantum mechanics says entangled particles exceed that limit. They match too often in some combinations and mismatch too often in others. The pattern is impossible to explain with any local hidden variable theory, no matter how clever or complex. The specific numbers matter here. Bell's inequality sets a maximum correlation value of 2 for local realistic theories. Quantum mechanics predicts a value of approximately 2.8 for optimally entangled particles. That's not a small difference. It's a clear, measurable violation that experiments can test. This is what makes Bell's theorem so powerful. It's not vague or philosophical. It's a precise mathematical prediction. You can design an experiment, run it, calculate the correlation values, and see which prediction matches reality. Either the correlations obey Bell's inequality, supporting Einstein's local realism, or they violate it, supporting quantum non-locality. When scientists finally performed these experiments in the 1970s and 1980s, the results were unambiguous. The correlations violated Bell's inequality. The measured values matched quantum mechanics predictions almost perfectly. The universe does not follow local realistic rules. This means something profound about the nature of reality. Separated particles are not truly separate. The idea that objects only influence their immediate surroundings breaks down at the quantum level. Distance, in some fundamental sense, is not what we think it is. Einstein was wrong, not about relativity, not about the speed of light as a cosmic limit for signals, but about the deeper structure of reality. The universe is not made of independent, separate parts following local causes. It's an interconnected whole where measurement of one part instantaneously correlates with distant parts. This isn't speculation or interpretation. It's what the mathematics proves and experiments confirm. Bell's theorem shows that any worldview based on separation and locality cannot explain what we observe. The universe is fundamentally non-local. But here's the thing about mathematical proofs: they're only as good as reality. Bell's inequality made a testable prediction. Either experiments would prove him right, or quantum mechanics would need a complete overhaul. Bell's theorem made a testable prediction. Run the experiment, measure the correlations, and see if they violate the inequality. If they do, Einstein's worldview collapses. If they don't, quantum mechanics needs revision. The first serious test came in 1972. Stuart Friedman and John Clauser at Berkeley spent months building their apparatus, creating entangled photons, aligning detectors, running calibrations. Clauser had become fascinated by Bell's theorem after reading it in 1971, and he was determined to test it experimentally. They had one shot to answer a question that had haunted physics for decades. Is Einstein right, or is the universe genuinely non-local? They ran the experiment, they measured the correlations, they did the calculations, and then came the moment of truth. Would the numbers obey Bell's inequality, confirming that the universe is local and realistic? Or would they violate it, proving that something impossible is real? The results were unambiguous. The correlations violated Bell's inequality. The universe is not local. Quantum mechanics was right. And in that moment, Einstein's worldview, the worldview that had guided physics for decades, collapsed. But critics immediately pointed out loopholes. Maybe the detectors weren't efficient enough. Maybe information leaked between the measurement devices. Maybe the random number generators choosing the measurement angles weren't truly random. Each loophole offered a potential escape route for local realism. The most famous experiment came in 1982. Alain Aspect and his team in Paris designed a test that closed several loopholes simultaneously. They used fast-swipping equipment to make sure the measurement settings changed faster than light could travel between detectors. They placed the detectors far enough apart that no signal could coordinate the results. They improved detection efficiency to minimize sampling bias. The results were stunning. Bell's inequality was violated with overwhelming statistical significance. Quantum theory's predictions aligned perfectly with reality. Einstein's worldview was shattered beyond repair. But the detection loophole remained particularly stubborn. If detectors only catch a fraction of particles, maybe the ones they miss follow different rules. This led to decades of increasingly sophisticated experiments. Scientists used different particle types: photons, electrons, atoms, ions. They increased distances between detectors to hundreds of meters, then kilometers. They improved detection efficiency. They used cosmic sources for random number generation to ensure measurement independence. The breakthrough came in 2015. 3 independent teams in Delft, Vienna, and Boulder simultaneously published loophole-free tests that finally combined all improvements at once. Each experiment closed all major loopholes simultaneously. The Delft experiment used entangled electrons in diamond. The Vienna experiment used entangled photons separated by 60 meters. The Boulder experiment used entangled ions. All 3 violated Bell's inequality with overwhelming statistical significance. The combined evidence left no room for doubt. The scientific community responded with near universal acceptance. The 2022 Nobel Prize in Physics was awarded to Aspect, Clauser, and Anton Zeilinger for their experimental verification of Bell's theorem and pioneering quantum information science. The Nobel Committee's statement was unequivocal. Quantum entanglement and non-locality are real. These experiments didn't just confirm a theory. They revealed something fundamental about the universe. When you measure one particle, you're not discovering a pre-existing property. You're participating in an event that instantaneously correlates with distant particles. The correlation isn't traveling through space. It's not a signal. It's a manifestation of a deeper connection that transcends spatial separation. This has been verified across every distance scale tested. Entanglement survives in fiber optic cables spanning cities. It persists between ground stations and satellites in orbit. The correlation remains perfect whether particles are separated by meters or millions of kilometers. The experimental verdict is final. Bell's inequality is violated. Local realism is false. This isn't interpretation or opinion. It's measured, tested, proven fact. So what does this actually mean for the nature of reality? It means the universe is not made of independent objects following local causes. There's a deeper interconnection that precedes and underlies the appearance of separation. Think about that for a moment. Every person you've ever loved, every moment you've shared with them, at the quantum level, you remain connected, not metaphorically, not spiritually, literally. The particles that make up your body have interacted with the particles that make up theirs. And according to Bell's theorem, that connection persists across any distance. Distance, as we experience it, emerges from something deeper. Space might not be the primary reality. Connection might be. Separation is an illusion, a beautiful, persistent illusion, but an illusion nonetheless. And here's what that means. Everything you think is separate. You and me, you and the people you love, you and the universe is actually connected at the deepest level, not symbolically, not metaphorically, literally. The quantum evidence proves it, the math proves it, the experiments prove it. This is where physics meets the deepest insights of contemplative traditions. The scientific validation of non-locality confirms what mystics have described for millennia. Everything is interconnected. The universe is one undivided whole. So the next time you feel alone, remember this. At the quantum level, you're never truly separate. The people you love, the world around you, you're all woven together in ways that science is only beginning to understand. And that's not poetry. That's not spirituality. That's physics. That's reality. That's Bell's theorem proven.